Hello everyone, my name is Melanie Feist. Today I will introduce you to Rango, an intuitive rule language for learning classifier systems and cyber-physical systems. Learning classifier systems are a promising learning and self-adaptation approach for cyber-physical systems, thanks to their relatively low computational complexity and thus the ability to perform on devices with low computational power and the ability to making decisions in real time. The basis of learning classifier systems to achieve adaptation and learning are so-called rules. Rango is a language which is described by a context-free grammar to formulate rule sets in an intuitive, generic, and flexible way. Such a learning classifier system approach can be embedded in the well-known and used make-K loop architecture. The system state is received via a monitoring interface which forwards relevant information to the analyzer. The rule engine is then responsible for the rule evaluation and reward calculation. It compares the current system state to the condition clauses of the rule set stored in the knowledge component. All rules that are currently applicable are included in a match set. The planner selects the rule from the match set that is expected to lead to the highest reward, and the executor controls the application of the rule. Of course, the rules that describe potential adaptive behavior needs to be formulated. So far, often bit strings are used to codify the rules. But this is not advisable for the cyber-physical system use case, since first, the complexity of typical use cases would lead to lengthy bit strings that are unreadable and, more importantly, impossible to write by humans. Second, such bit strings cannot express certain conditions and actions that might be required in such cyber-physical system use cases. To overcome these issues, we introduce Rango. The language enables system administrators to systematically and formally create rules for a learning classifier system in an intuitive way. They can store rules written in Rango in a rule file. This rule file is automatically passed into an internal binary representation for the knowledge component. Also, Rango rule sets can be written back into the original human readable representation, including learned information. In the following, I describe Rango's features by applying it to a simplified automotive use case. Therefore, we assume a car with several electronic control units as processing nodes with a certain computational power and a learning classifier system instance. The communication among those echoes is realized by a typical vehicular communication channel like a CAN bus, and each echo is responsible for various car functions such as brake control, cruise control, and so on. Also, each application has predefined requirements such as timing constraints. Now, when we go on a journey with a car, the number of active and required applications can vary during this journey. For example, we might need to start the navigation system due to a road closure on our way. This potentially leads to an echo overload if the echo on which the navigation application is started does not have sufficient computational power to cope with the increased demand. As a consequence, the applications on this echo may fail to meet their requirements. If the communication channel within the system has enough capacity for additional communication, a relocation of the navigation to one of the other echoes might be a suitable application action. Of course, the relocation adaptation action is only one option. There might be other adaptation actions that are even better. This is just an example. Now let's see how we can formulate such a desired relocation adaptation rule with Rango. In general, a rule consists of a condition and an action. Thereby, conditions and actions can either be specified directly or defined and referenced by name. Here, the condition is referenced with the name relocation might be useful, and the action is referenced with the name relocate local unhealthy apps. There are two things to note here. First, the reference by name allows system administrators to use an action or condition multiple times in a rule set without having to rewrite it. In addition, this increases the efficiency of rule evaluation, since a condition or action that is used multiple times only needs to be evaluated once. Second, dimension of health. In the language, health is a normalized value to express the system condition, with 1 as the best possible health and 0 as the least acceptable health value. The condition of a component and the whole system can then be expressed by multiple of such health values. For example, if a app can't fulfill its demands or timing constraints, it becomes unhealthy. Similar, a node may become unhealthy when it gets overloaded. To be able to reference a condition or action by name, we first need to define it. Here we can see an example definition of the relocation might be useful condition. This example shows that a condition consists of a conjunctive link of subconditions. Such subconditions always operate on sets. A set can exemplarily contain applications, nodes, or communication channels. The cardinal keyword here delivers the cardinality of the sets. In addition to the cardinality, the maximum, minimum, or average value of one of the sets attribute can be used for comparison. In the provided example, the cardinality of 4 sets, local unhealthy apps, local unhealthy nodes, non-local suitable nodes, and local unhealthy comms, is used to specify subconditions. The overall condition relocation might be useful, therefore evaluates to true if the first 3 sets are non-empty, while the last one is empty. Thus, this condition checks whether there are local unhealthy applications, meaning applications where they're not meeting their requirements, are running on a local unhealthy node, meaning an overloaded echo, while the communication is still healthy, and there are other suitable nodes with remaining capacity to which the unhealthy application can be migrated. Similar to condition and actions, the sets in the condition on the previous slide are again referenced by name, which makes them reusable in different condition and actions. Of course, they can also be specified directly in the condition. Anyway, the sets, when we use the reference, need to be defined. They can be defined by direct referencing, for example, applications, nodes, or communication channels by name. Or sets can be defined via queries. Defining sets via queries makes it possible to keep the rules independent of specific applications or use cases. Instead, these sets are constructed dynamically based on the respective query. In a query, attributes can be compared to an arbitrary value, or the maximum or minimum value can be requested. Here, we exemplarily define 2 sets used in the previous condition. The local unhealthy app set includes all local unhealthy applications, meaning those with health values of 0, since this means that they don't meet their requirements anymore. The second set, non-local suitable nodes, contains the healthiest non-local node with sufficient remaining computational power. Finally, we need to define the action to be able to reference it by name. As can be seen on our example here, the action reuses the sets that we have already defined for the condition, together with a cyber-physical system-specific keyword relocate. As seen in the example, Rango includes several cyber-physical system-specific keywords for components, attributes, actions, and scopes. Our little example only contained a small subset of those. Those are underlined here in the table. This table here shows a few more of the keywords, but still not all. Hopefully, this shows a little bit how powerful and flexible Rango is to express rules, even when there's no time to go in full detail of the language capabilities. Now let's take a look at how we evaluated Rango. We evaluated Rango in 3 aspects: its performance, usefulness, and usability. In terms of performance, we analyzed the memory requirements to store the binary representation of the rule set and the computational complexity for the rule set parsing at system startup, and rule evaluation during runtime. It shows that Rango introduces only a marginal overhead and a linear runtime complexity. The detailed analysis can't be found in the paper. To evaluate if Rango has a practical worth for potential users and is useful, we designed an online questionnaire and consulted 5 learning classifier system experts. Each of them had to rate how difficult it is to define an initial rule set for a learning classifier system and to interpret output of the learning classifier system for experts like themselves and system administrators. First, without the use of Rango, and after a short introduction to the language like we have given in this presentation, with Rango. Unfortunately, due to timing constraints, I can't get into detail with the results. So just let's sum up that overall, all ratings improved with the option to use Rango as a rule language. To evaluate how easily potential users understand and create rules in Rango, we again designed an online questionnaire. First, the participants were confronted with an CPS use case and corresponding code in Rango that would achieve the described adaptation. The task of the participants was to understand the code step by step and to answer multiple choice and open questions. Thereby, we labeled the participants' answers to the multiple choice questions either with correct or incorrect. The answer to the open questions with regard to understanding rules were categorized into correct, inaccurate, and incorrect. Afterwards, participants were confronted with the use case I explained in this presentation. The task of the participants was to write the rule and its required condition, action, and sets step by step by themselves. A textual guidance leads the participants through the coding process, and explanations of the Rango syntax in a format similar to typical programming language tutorials were provided. The results of the study shows that understanding the code step by step and answering multiple choice questions and open questions achieve a high percentage of correctness. This leads to the conclusion that rules written in Rango are easy to understand and that no explicit syntax briefing is required to be able to understand rules. In the written part, in each step, a small number of minor syntactic mistakes were made. However, in practice, the parser would note these errors and the user would get a notification to correct the syntactic mistakes. So we count them as correct in the following. Furthermore, only in the definition of sets, semantic mistakes were made. One common mistake was the usage of the wrong scope for the set specification, but those scopes were not explicitly explained to the participants in the questionnaire and the Rango explanation. In addition, the results show that the definition of the condition and sets is more demanding for the users. Still, more than half of the participants, to be exact 55.3%, correctly defined a difficult set. The easier sets were correctly defined by 64.4%, and the condition was formulated correctly by 73.7% of the participants. The definition of the action was correctly by 92.1%, and nearly all participants defined the rule correctly. Finally, this leads us to the conclusion that even non-experts are easily able to create rules in Rango. In this talk, I have introduced Rango, an intuitive, flexible, and powerful rule language for learning classifier systems and cyber-physical systems. We started the journey with a short introduction to self-adaptation with learning classifier systems and the need for a language to formulate rules in a comfortable and powerful way. Afterwards, Rango's features were described by applying it to a simplified automotive use case. Finally, I presented some results of our extensive evaluation, which proves that Rango introduces only marginal memory and computational overhead, is perceived as useful by learning classifier system experts, and is intuitive and therefore usable even to non-experts. We have reached the end of my presentation. Thank you for your attention.